A model with 35 billion parameters just beat a model with 397 billion on every single coding benchmark its makers published. Not one, not most, all 9. And before we go a step further, I want to kill the ambiguity in that sentence, because there is one and it matters. The 397 billion model being beaten here is Qwen 3.5's flagship, a different lab's largest open model. The lab that built the small one also ships a 397 billion model, and theirs scores considerably higher than the small one does. So this is not a case of a company's little model embarrassing its own big model. It's a case of a small model from one lab outcoding a big model from another, and the gap is 11 times in total parameter count. Now, here's the part that makes this a video rather than a table. The small one only activates about 3 billion parameters per token, and the 4-bit build of it is 21.7 gigabytes, which means the weights fit on a single 24GB consumer graphics card, the kind that sits in a lot of desktops right now. So the question that runs underneath everything today, how does a model that's small get that good at coding? Because it isn't more parameters, it isn't more data in the ordinary sense, and it isn't a bigger training run. It's something else, and the lab published exactly what, in detail with the reward functions written out. 3 things. First, the numbers and precisely what comparison they represent, including the 4 benchmarks where this model clearly loses, because a 9 from 9 sweep in one category sits next to some real defeats in another, and you should hear both from the same person. Second, the mechanism, which is the actual story here, and the reason this isn't just another leaderboard post. The model generates its own training tasks. It builds its own test harnesses for those tasks. It solves them, and all 3 of those stages get trained together. There's one number buried in that section that I think is the single most interesting thing published this week. And third, running it, the quantized sizes, what genuinely fits on a card you might own, and the honest gap between the weights fit and you can use it at full context, because those are not the same sentence. Standards note, every figure today is the lab's own published number, averaged over 5 independent runs by their own account. Read from their blog post and model card this morning. I have not run this model, reproduced a benchmark, or measured anything. When the numbers are theirs, I'll say so, and I'll say it more than once. Let's go. What this actually is. The shape first, because it explains a lot. This is a family at 3 sizes. A 397 billion mixture of experts model at the top, the 35 billion mixture of experts model we're discussing in the middle, and a 9 billion model at the bottom, plus a quantized mobile build of that 9 billion, which the blog says can be readily deployed on iPhone and Android devices. The license on the model card is MIT, which is about as permissive as licensing gets. And one line of lineage that you should know before you form an opinion, verbatim from the blog. This family extends Ornith 1.0, which was developed on top of Qwen 3.5 and Gemma 4, with additional continued pre-training, mid-training, and post-training. So this is not a model trained from nothing. It's built on top of 2 existing open model families, with substantial additional training on top. The architecture string on the download page even names its inheritance directly. That's not a criticism. Building on open foundations is exactly what open weights are for, and the additional work here is clearly enormous. But it does mean the MIT license on this card sits on top of Upstream licenses. And if you're shipping something commercial, the Upstream terms are worth reading yourself rather than assuming the top-level label covers everything underneath it. 90 seconds of reading against a business decision. Now the mixture of experts part, because it's why the hardware story works at all. In a standard model, every parameter participates in every token. In a mixture of experts model, the parameters are divided into many specialized groups, and a router picks a small subset for each token. So this model contains 35 billion parameters. You have to store all of them, but only about 3 billion of them fire for any given token. That's the trade. You pay full price in memory and a small fraction of the price in computation, which is precisely the trade that suits a local machine, because a desktop card is usually far more constrained on memory than it is on raw arithmetic. A mixture of experts model is a big model that behaves like a small one at the moment of use. And that is why a 35 billion model can feel quick on hardware that would struggle with a standard model half its size. The numbers, and the ones that go the other way. 9 coding benchmarks, all theirs, all 5 run averages. Terminal bench 2.1, run through one harness, 67.8 against 53.5. Run through a different harness, 68.5 against 48.6. SWE-bench Verified 79 against 76.4. SWE-bench Pro 59.6 against 51.6. Multilingual 71.4 against 69.3. NL2 Repo 46.2 against 36.8. SWE Atlas QnA answering 39.8 against 20.4, nearly double. And then the row that stopped me. DeepSWE 22 against 1. That's not an improvement, that's a category change. And it's more striking inside their own line. Their previous 35 billion model scored 0 on that benchmark. 0. One generation later, 22. A benchmark that was completely out of reach for this size class is now partially solved by it. Frontier Bench shows the same shape at a smaller scale. 5.1 against 1.4, up from 1.4 in their own previous version. So, 9 from 9, against a model 11 times its size, with 2 of those wins being step changes rather than increments. Now the other direction, because it's the same table. On reasoning and search, this model loses and not narrowly. Humanities last exam with tools, 33.4 against 48.3. That's a 15-point deficit. Browse comp, 67.6 against 78.6. Wide search, 67.8 against 74. And on one agentic benchmark, it's beaten by a 30 billion standard model, 70.2 against 75.5. Which tells you exactly what this is. It is not a small model that became a frontier model. It is a small model that became extremely good at one thing, writing and fixing code inside a repository, using tools over long horizons. On broad reasoning and open-ended web research, it remains a 35 billion model, and it performs like one. That distinction should decide whether you download it. If your work is coding agents, this is remarkable. If your work is research and synthesis, the big models are still the big models, and no amount of clever training has changed that yet. The other two sizes, briefly, because one of them matters more than the headline. The family has 3 members, and the middle one is only the one we're discussing because of the hardware sweet spot. The other 2 are worth a beat each. At the top, the 397 billion version scores 86.1 on Terminal Bench and 56 on DeepSWE, which their blog places on par with Claude Opus 4.8 at 85 and 59. It beats the other leading open models of similar scale on both, though note the honest ceiling in their own table. A 2.8 trillion model still sits above all of them at 88.3 and 67.5. Frontier adjacent, not frontier leading, and their table says so. At the bottom is the one I find most interesting, and it's the one that fits this channel's actual audience. The 9 billion model scores 46.2 on Terminal Bench and 70.6 on SWE-bench Verified. Sit with the second number, 70.6 on SWE-bench Verified from a 9 billion parameter model that beats a 31 billion standard model outright, 52, and comes within 3 points of a 35 billion mixture of experts model, on a benchmark that was, not very long ago, a frontier model benchmark. And the blog says there's a quantized build of it that can be readily deployed on iPhone and Android devices. A model that resolves real repository issues on a phone. That's the sentence. And if it holds up under independent testing, it's a bigger story than anything in the headline table, because the 35 billion needs a good graphics card and the 9 billion needs a pocket. The mechanism how a small model got there. Here's the actual story, and it's the reason this release matters more than its table. Most training pipelines have a fixed shape. Humans curate a set of tasks. Humans design the harnesses that check whether the model solved them, the model attempts them, gets rewarded, improves. When the model outgrows the task set, humans go and build a harder one. This lab removed the humans from 2 of those 3 jobs. Their description, verbatim, the model proposes new tasks, generates task-specific scaffolds, and produces solution rollouts for reinforcement learning, continuously creating new learning experiences from which it can improve. 3 stages per cycle. First, given an environment and its own history of what it has already solved, the system proposes new tasks that go beyond what it can currently do, deliberately aimed at exposing capability gaps. Second, for each task it generates a scaffold, and the blog is specific about what that means. The instructions, the tools, the decomposition strategy, and the orchestration used to approach the problem. In other words, the model designs the agent harness it will be judged inside. Third, it produces solution attempts. And the piece that ties it together, verbatim, reward from the rollout is propagated across all 3 stages. So the system learns not only to produce better solutions, but also to generate more useful training tasks and construct more effective scaffolds. Read that again. It is not just learning to code better. It is simultaneously learning to write better exam questions and to build better exam rooms. Because all 3 get graded by the same outcome. That's the loop, and it's genuinely different from a model that simply trains on more data. And the strongest evidence that the loop does something is in their own line, not against rivals. Compare this version to the previous one at the identical size, same lab, same parameter count. DeepSWE went from 0 to 22, Frontier Bench from 1.4 to 5.1, SWE Atlas question answering from 37.1 to 39.8, Terminal Bench from 64.2 to 67.8. That comparison is the useful one, and it's the one this channel always reaches for first, because a self-delta holds most variables still. Same size, same lab, same benchmark suite, same harnesses, 1 generation apart, with the stated difference being that the self-improvement loop was extended from optimizing scaffolds and solutions to also optimizing task generation. If you want to know whether generating your own curriculum works, that row is the experiment. 0 to 22 on a benchmark the previous generation could not touch at all is the kind of jump that either means the method works or means something in the evaluation changed. Their footnotes say the harness and settings were held constant. I can't verify that from here, but I can tell you it's the number I'd check first if I could. The number I keep thinking about. Now the detail I promised, and it's a single value in the reward function. If you let a model invent its own training tasks, the obvious failure is that it generates tasks it can already do. Free reward, no learning. So the reward has to prefer tasks at the edge of what the model can manage, and the question is where exactly you put that edge. Their answer? They sample multiple attempts at each proposed task, measure the empirical success rate, and reward tasks whose success rate sits near a target. That target is 0.2, 20%. They are deliberately training on tasks the model fails 80% of the time, and their reasoning is stated plainly: it favors tasks that are challenging but still yield enough successful trajectories for reinforcement learning. Fail everything and there's no signal to learn from. Succeed at everything and there's nothing to learn. 20% is the sweet spot between those two failures. And then the sentence that makes it self-sustaining verbatim: as the model improves and solves a task more reliably, its reward naturally decreases, pushing the generator toward harder problems. The curriculum escalates itself. The moment a task becomes easy, it stops paying. So the generator is pushed to invent something harder. Nobody has to notice the model outgrew its training set and go build a new one. The reward function notices automatically, and the frontier moves. That is a small piece of design with a large consequence. And it's the most interesting thing I've read this week. Two guards sit alongside it. Validity, which checks that a proposed task actually forms a working environment. The scaffold runs, good solutions pass, bad solutions fail, and the evaluation matches the specification. It can be applied as a hard gate, and their stated reason is exactly right: to stop malformed tasks or unreliable scaffolds from receiving reward simply because they appear difficult. Without it, the easiest way to generate a hard-looking task is to generate a broken one. And novelty, measured against a buffer of previously generated tasks, to stop the generator producing 1,000 variations of the same problem. Though they're careful to note novelty stays secondary, the goal is reducing redundancy, not rewarding weirdness. And here's the structural detail. Those three signals are multiplied together, not added, which means a task scoring 0 on any one of them scores 0 overall. You cannot compensate for an invalid task by making it very novel, all three or nothing. Rewarding a test for being hard to cheat. One more piece, and it's the one I'd point at if someone asked why this lab looks serious. The generated harness gets its own reward, with 3 components. Does it faithfully reflect the task specification? Do its rewards track the true quality of solutions? And, verbatim, its resistance to evaluator failures, shortcuts, and reward hacking behaviors. They are explicitly rewarding the exam for being difficult to cheat. Think about why that has to exist. If a model designs both the test and the answer, the shortest path to a high score is a test with a hole in it. Any self-improving system that grades itself will find those holes, because finding them is easier than solving the problem. So the harness reward has to actively punish exploitability, or the whole loop optimizes itself into meaninglessness. Naming that as a reward term in public tells you they hit the problem and had to engineer around it. And that same instinct shows up in how they benchmark Git history stripped from repository images to prevent access to prior solutions or commits. Network access disabled during evaluation, and for one benchmark, access to the relevant repositories and packages blocked outright to prevent reward hacking. Every benchmark row also names its harness, its temperature, its context window, its timeout, its hardware, and how many runs were averaged. 2 of the rows even name the model used as the judge. That is the level of disclosure that makes a number checkable rather than merely impressive, and it's rare enough to be worth pointing at. Running it, what actually fits. Now the practical part, and I want to be precise, because there's a gap here that will cost people an evening. The quantize builds from the download page. The 4-bit build is 21.7 gigabytes, 5-bit is 25.3, 6-bit is 29.2, 8-bit is 37.8, and the full 16-bit weights are 71.1. So the headline, at 4-bit, the weights fit on a single 24GB card. And because only about 3 billion parameters activate per token, it should generate at a speed that belies its size. 2 commands in the documentation get you there. One through the popular local runner, one through the local server, both pointing straight at the quantized repository, no conversion step. And now the caveat, which the lab states themselves. Their own serving guidance says the full precision model is roughly 70 gigabytes and recommends 2 80GB cards to leave headroom for the full 256,000 token context. Both of those things are true at once, and the reconciliation is the part nobody mentions. 21.7 gigabytes is the weights. It is not the whole memory bill. A model's context also has to live in memory, and that cost scales with how much context you ask for. So on a 24GB card, 4-bit weights leave you a little over 2 GB of headroom, which is a working context window, not a 250,000 token one. The honest version, you can absolutely run this on 124GB card. You cannot run it at its maximum advertised context on 124GB card. Set your context to what your work actually needs and it fits comfortably. Ask for the full window and you'll need considerably more hardware. Anyone telling you otherwise is quoting the file size and stopping. 2 more practical notes from the documentation. It needs recent runtimes, specific minimum versions of the 3 main serving frameworks are listed, and an older install will simply fail. And the lab mentions they modify the chat template to keep training and inference consistent, which is the kind of detail that produces mysteriously bad results if your tooling uses the wrong one. Honest limits. 5. 1. Every number here is the lab's own. Their benchmarks, their harnesses, their 5-run averages, their choice of comparisons, reproduced by nobody on this channel. The disclosure is unusually good, which makes them checkable, but checkable is not checked. 2. I have not run this model. No tokens per second, no quality judgment, no measurement of whether it's pleasant to work with. The arithmetic on what fits is arithmetic. Everything else is a reading of documents. 3. The comparison set is theirs. A 9 from 9 sweep is impressive, and it's also true that a lab picks which columns appear in its own table. The losses I quoted are in that same table to their credit, but a benchmark that appears in nobody's table tells you nothing either way. 4. The lineage matters for licensing. This is built on top of 2 existing open model families. The card says MIT, the upstream terms are their own documents. If money depends on the answer, read them, rather than taking a label, or my summary of a label, at face value. 5. This is days old. Downloads are already in the tens of thousands, and the collection was updated within the last day. Quant builds get revised, templates get fixed, and runtime support improves week by week. Check current documentation rather than trusting a video, including this one. Step back, because there's a bigger claim underneath the table. For most of the last 3 years, the reliable way to make a model better at something was to make it bigger or to feed it more of the thing. Both work, and both are expensive, and both eventually run into the same wall. You run out of good tasks. There are only so many well-specified, verifiable problems with reliable graders in the world, and the frontier labs have been consuming them at industrial rates. What this lab is proposing is a way around that wall. If the model can generate its own tasks, build its own graders, and have a reward function that keeps steering it toward problems at the edge of its ability, then the training set is no longer a finite resource you buy. It's something the system manufactures as it goes. And the evidence they're offering is exactly the shape you'd expect if that worked. Not a broad improvement across everything, but a dramatic improvement in the areas where tasks can be automatically generated and automatically verified. Coding, terminal work, agentic sequences, places where did it work has a machine checkable answer. Meanwhile, on open-ended research and reasoning, where correctness is a judgment call, the same model stays where its size says it should. That pattern is not a weakness in the story, it's the strongest evidence for it. A self-generated curriculum should help most exactly where tasks can be auto-verified, and that is precisely where the gains landed. Which gives the sentence to carry out of this. The bottleneck was never the model, it was the supply of good problems, and a system that can invent its own problems has just changed what running out of training data means. So here's my question, and I'll pin it below. If you run this on a 24GB card, what context length did you actually settle on, and what tokens per second did you get? Model quant, card context, speed. Because the gap between the weights fit and it's pleasant to use is where every local AI recommendation quietly falls apart. And a list of real numbers from real desktops is worth more than any table any of us can publish, including theirs. Every link, the technical blog post, the model card, the quantized download page with the file sizes, and the 2 commands that get it running locally is in the description. That's the standard here. The comparison stated precisely so the title can't be misread. The losses read out from the same table as the wins, the numbers labeled as the lab's own every time. The mechanism explained rather than admired, and the difference between what fits and what runs made explicit before anyone spends an evening on it. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.